Here is a question that reveals whether a Kotlin multi-platform project is built well or just hacked together. Where do your objects come from? If the answer involves the word singleton scattered across 15 files, or a companion object returning the same database instance on 3 different platforms, the architecture is already fighting you. Dependency injection is the practice of building objects in one place and receiving them where needed. In a multi-platform project that runs on Android and iOS from the same codebase, DI has to work across both platforms without forking into separate wiring graphs. Koin is the library that makes this possible. It is lightweight, pure Kotlin, and it starts in 3 lines. In this episode, we walk through exactly how the EurostatApp wires its entire object graph with Koin, one container that boots the same module list on Android and on iOS, with only the platform-specific driver factories differing. If you come from Android development, you probably know Hilt. Hilt is excellent on Android. It generates code at compile time using annotation processes and integrates deeply with the Android lifecycle. The problem is that annotation processes are a Java toolchain feature. They do not run in the Kotlin native compiler that produces iOS binaries. This means any DI framework that depends on capt or caps for code generation cannot share its module definitions in CommonMain. You end up writing 2 separate DI graphs, one for Android, one for iOS, and keeping them in sync manually. Koin avoids this problem entirely. Koin modules are plain Kotlin lambdas. They live in CommonMain and compile to every target. There is no code generation step. The trade-off is that Koin does type resolution at runtime rather than compile time, so a missing binding fails at startup, not at build time. For most projects, that is an acceptable trade. A Koin module is a DSL block. You declare bindings with 2 keywords. Single creates 1 instance for the lifetime of the Koin container, effectively a singleton. Factory, a new instance every time the dependency is requested. Inside each block, the get function resolves another dependency by its type. That is the complete core API. You start Koin by calling startKoin, passing a list of modules. From that point, any code inside the container can resolve dependencies using inject or get. There is no annotation on every class. There is no constructor magic. You write plain Kotlin class constructors and Koin calls them. This makes the dependency graph easy to read. Every binding is visible in the module file, not scattered across annotations on the classes themselves. The price you pay is that if a binding is missing, you find out at runtime on the first inject call, not during the build. The EurostatApp has 16 modules, 8 feature modules and 8 core modules. Each feature module owns its own Koin module definition in a D subfolder. Open feature population and you will find feature population module.ectd with a single top-level function that returns a Koin module. It binds the API service as a factory, the cache DAO as a factory, the repository as a single, the use case as a factory, and one special entry, the component factory registered with a qualifier. Each feature module can be understood in isolation. The population module does not know about the economy module. The economy module does not know about population, because Gradle enforces this with build boundaries. These modules do not depend on each other. The DI isolation is a direct reflection of the compile time isolation. When a new feature is added, a new module file is written and 1 line is added to the app-level aggregation. Nothing else changes. The distinction between single and factory matters most at the repository layer. A repository holds a reference to the cache DAO and has internal state about ongoing requests. Creating a new repository on every inject call would throw away that state and potentially start duplicate network requests, so repositories are registered as single. Use cases, by contrast, are stateless wrappers around the repository. They hold no mutable state, they just delegate. Creating a new use case instance per injection is free and avoids any accidental cross-feature state leak, so use cases are registered as factory. The API service and the cache DAO sit in the middle. They carry no mutable state themselves, but they wrap objects that do, the HTTP client and the database driver, which are registered as single in their respective core modules. The feature-level bindings for API service and DAO are factories because the real cost lives in the core singletons they receive via GET. The most interesting binding in the entire codebase is the ComponentFactory. Decompose requires a function that takes a component context and returns a component instance. That function cannot be called at DI graph construction time because component context is not available until navigation happens. Koin handles this through factories. A factory lambda is called at the moment of injection, not at startup. The challenge is that all 8 feature modules register a binding of the same type, ComponentFactory of Any. Koin needs to distinguish between them. This is done with named qualifiers. Each feature module registers its component factory under a qualifier derived from the class name of its child config entry. The root component then resolves the correct factory by looking up the class name of whatever config it needs to instantiate. This pattern means adding a new feature to navigation requires 0 changes to any existing module, only a new qualifier in the new feature's DI file. The AppModules function lives in the nativeAppMain source set, which is an intermediate source set shared by Android, iOS, and desktop but not by WASM JSONs. It returns a flat list of all module definitions, core first, then feature modules. This is the single file in the project where every module is known. Adding a new feature module means adding one import and one line to this list, nothing else. The order of the list matters only if 2 bindings have circular dependencies, which should not happen in a well-layered architecture. Core modules are safe to list first because feature modules depend on core, never the reverse. The appModules function is called from both the Android application class and the iOS Koin initializer. Both platforms receive exactly the same module list. The only platform-specific addition is the database driver factory, which is appended outside of appModules because it requires a different constructor on each platform. On Android, Koin starts inside EurostatApplication, which extends the Android application class. The override of onCreate calls startKoin with the result of appModules, plus an extra anonymous module that registers the database driver factory. The Android version of database driver factory. The Android version of database driver factory takes a context as its constructor argument. The context is resolved with get because Android context was registered when Koin started. That is the job of the Android context call in the startKoin block. There is a guard at the top of onCreate. If global context already has a Koin instance, the function returns early. This guard exists because Android can reuse the same application process for isolated services, and calling startKoin twice would crash. The guard costs nothing in the normal case. On Android, the application class is declared in the manifests, so EurostatApplication is instantiated by the system before any activity or service is created, making it the correct and only place to start Koin. On iOS, there is no application class. The entry point into the Decompose multi-platform layer is a UIViewController factory function called MainViewController. The first line of MainViewController calls init_KoinIOS. The init_KoinIOS function mirrors the Android startup exactly, but without the Android context call, iOS does not need it. The database drive factory for iOS takes no constructor arguments because the iOS SQLite driver does not require a context. The same guard pattern is used. If Koin platform already has a Koin instance, the function returns immediately. This guard handles the case where the framework reinitializes the view controller, which can happen in SwiftUI previews or certain background scene configurations. Beyond these two small differences, no Android context, no arg driver factory. The iOS Koin startup is byte for byte identical to Android. Same modules, same bindings, same resolution behavior. One module list, two platforms, zero divergence in the object graph. The correct way to test with Koin is to not use Koin in unit tests at all. Unit tests should construct their subjects directly, passing fakes for dependencies in the constructor. If your repository test calls startKoin, you are writing an integration test, which has its place, but it is not the first line of defense. The Eurostat tests follow this pattern. Population repository platitei constructs a population repository platically, passing a fake population ability service, a fake population cache DAO, a test batcher provider, and a fake lock. No Koin involved. The fakes are short-handwritten implementations of the interfaces, not generated mocks. Mockk is not used because Mockk does not work on Kotlin native, which is the iOS runtime. If you use generated mocks in common tests, your tests will compile but fail on iOS. Handwritten fakes are 4 to 8 lines each and make the test contract explicit. Koin is tested implicitly through the integration path, smoke tests that start the real container and check bindings resolve without error. 3 mistakes appear in almost every KMP project that adds Koin for the first time. First, instantiating the HTTP client multiple times. Each Ktor client on iOS holds Darwin URL session resources. If you register the client as a factory instead of single, every repository request leaks a session. Register HTTP client as single, every repository request leaks a session. Register HTTP client as single in the core network module. If a binding inside AppModules calls get of type context, the binding will crash on iOS because no Android context was registered there. Keep context-dependent bindings outside AppModules in the platform-specific extras passed to startKoin. Third, missing bindings discovered at runtime. Because Koin does not verify the graph at compile time, a typo in a qualifier or a missing module line will crash at startup. The mitigation is a check modules test, a Koin utility that instantiates every binding in a test environment and fails if any resolution throws. This brings the verification forward to CI. Koin is not the most powerful dependency injection framework available for Kotlin. Dagger and Hilt produce compile-time verified graphs and have zero runtime overhead for the resolution itself. But compile-time verification requires annotation processes that do not work in Kotlin native. That is not a theoretical limitation, it is a hard toolchain constraint today. Koin's runtime resolution is fast enough for all practical purposes, and the module DSL is readable enough that the graph is verifiable by inspection. The pattern we walked through today feature modules as isolated Koin module files, a single aggregation point in nativeAppMain, platform-specific driver factories added outside the shared list, handwritten fakes in tests, is directly portable to any Kotlin Multiplatform project. Clone the Eurostat repo, open feature.module.act3, add a quid, and you have a working template for every feature you add. If this episode was useful, subscribe for more on Android and Kotlin Multiplatform.